Hello everyone. Welcome to the 2021 ACOM seminar series. It's an honor and a pleasure for me today to introduce Dr. Matthieu Riva. He's a permanent research faculty member at CNRS, Lyon, France. And he works in collaboration with Christian George within the catalyst and atmospheric reactivity for the environment or CARE team. Matthieu got his PhD in analytical chemistry and environmental sciences at the University of Bordeaux, France. He did one postdoc in the US at the Gilling School for Public Health at the University of North Carolina, Chapel Hill, and the second at a familiar place to me, the Department of Physics of the University of Helsinki in Finland. His research focuses on understanding the chemical formation and evolution of secondary organic aerosols in the Earth atmosphere. He uses and develops advanced mass spectrometric technique to study the chemical processes involved in the formation and growth of newly formed particles in the atmosphere, and he studies the gas phase chemistry of highly oxygenated organic molecules, or HOMs. Today he's going to tell us how he developed and used the chemical ionization Orbitrap to study atmospheric reactive organic species and the formation of new particles. Before starting, I would like to remind you that today we have a slightly different format. If you are joining via streaming, not much has changed. There is a space for typing in your questions that will be read by me at the end of the talk, but you can type the questions at any time. And we will have some ACOM people joining via Zoom that will be able to ask the question directly to Matthieu in person. We'll see how that goes. It's a new experiment for me today. And with that, I introduce you to Dr. Riva. Matthieu, please take it away.
Thank you, Ale, and good morning, everyone. So as Ale mentioned, and today I'm gonna present like the development of the CI-Orbitrap that we started in Lyon in 2018. So a brief kind of history of like why we developed the CI-Orbitrap, or what motivated us to develop the CI-Orbitrap was, or the idea came when I was like a postdoc with Mikael N at the University of Helsinki, and then as you probably know, that we are quite interested, or we are quite interested in the ozone analysis of alpha-pinene. And so we did like a bunch of chamber experiments, and when we were developing new reagent ion and then playing with the different mass spectrometers, then we were facing kind of exciting results, but also like very complex results. Because if you oxidize basically ozone or alpha-pinene with ozone, then you produce a very, very complex and difficult set of like oxygenated volatile species. And this is like an example of like the complexity of the chemical reactions. Like I'm displaying the mass defect plot. So for those who are not familiar, that's a difference between the theoretical mass and then the measured one. So it's kind of a 3D dimension. On the x-axis, you have the master charge, and on the y-axis, you have the difference between the theoretical and then the measured mass. And then you can see that like from the one simple reaction, then you can produce like close to like 1,000 or 1,500 like molecules or ions that we were able to measure. This mass effect is coming from the amine CIMS. So the amine CIMS, like for those who are not very familiar with mass spectrometry and like CI measurements, it's basically so in this study where we were like comparing the capabilities of the different mass spectrometers and then the capabilities of different reagent ion to capture the different species. So the amine CIMS is the mass spectrometer that like, or the CI that is in blue in shaded regions, and then on the y-axis is the compounds from like the precursor, which is alpha pinene in that case, to like very oxidized compound. And you can see that like basically with this compound, then we were able to capture a very, very wide variety of compounds. If you start playing with different reagent ions, then you can be more specific. And then the problem of the CI can be like reduced. For instance, if you use a PTRMS or normal variety of PTRMS, and basically you see that like then the variety of compounds is limited, so you are less, the complexity of the chemical reactions are less problem. But if you start capturing more and more compounds and more oxygenated species, then the lack of resolving power is quite limited. So just a quick reminder of what I call chemical ionization. So maybe more, some of you are using the IMS. So the IMS is using the EI technology, which is basically transfer the energy of an electron to ionize the molecules. In our case, when I call CI, it's an indirect process that we form what we call a reagent ion, so a molecule capable of ionizing a molecule, and this molecule will be ionized by either proton transfer. So basically, a proton that is created will be transferred to the molecule, to the analytes. But also, you have like some adduct formation, and those are adduct formation in case of nitrate. Then nitrate will go from the dimeric compounds to the analyte to form the ion. So it's a way that we form the ions. This is, there are some advantages because then it's recognized to be soft. So on the top, then you have basically mass spectrum obtained with EI, so very hard ionization. So you can see that the molecules are fragmenting in small fragment ions. But then if you, oops, I'm sorry, my PowerPoint crashed. I'm gonna try to restart it. Sorry for that. So it's going to take a few
Matthieu,
minutes.
if you have problem, you can also send me your presentation, and I can.
Yeah, just because the presentation crashed basically. So.
Mm-hmm.
Okay. Okay, so basically the go back.
I'm sorry, Matthieu, can you share your screen again?
Oh, sorry. Why is the Zoom? Okay. Give me just 2 minutes because I think it's also because my battery is running low. Sorry about that. Okay, sorry about that. So basically what I was saying that like is when you do CI, you preserve the identity of the molecular ions. So then it's much easier to do some peak identification. So one of the limitations that I was mentioning a bit earlier is the difficulty of retrieving the chemical composition of the ions that we are measuring. So here it's a displaying of mass spectra ionized or observed or formed with nitrate reagent ions. So with this kind of ions, you can see that you have, even with a most resolved like a mass analyzer, which is the TOF of the resolution of 10,000, then you can see that basically that there is some overlapping peaks. So for instance, here you have at the mass to charge 310, then you have overlapping peaks. And then you have some peaks, some very tiny one that will be very hard to retrieve the chemical identity, or to even believe that they are present. And if you go to like even bigger masses, then you can see that you have many overlapping peaks, and it's getting very hard to retrieve and to make 100% sure that the compounds are here. And then this is like with nitrate reagent ions. So for those who have done like nitrate reagent ions, it's probably one of the easiest CI to use. But if you go, for instance, for more the versatile type of mass spectrometers, so for instance, the PTR3 with a lower resolutions, then you can see that like it starts to be almost impossible to really be 100% sure that the resulting peak that we have, and then the amount of peak that we are using, of ion that we are using to explain the signal recorded by the mass spectrometers are present or not. And this is like an example of like some oxygenated species, so observed with the PTR3, and then you can see that there is probably 10 to 15 different peaks present, or that has been proposed to explain the signal recorded by the mass spectrometers. So one idea at the time, and then we were looking at the data, and then also trying to characterize all the oxygenated species that we observe in the smoke chamber. That was like, it would be great if we can greatly improve the sensitivity and then the mass resolving power of the mass spectrometers. So this is what we started to do by taking the advantage of the Orbitrap. So this is basically a schematic of the Orbitrap. So instead of like going into detail on that, then I will just show you a quick videos from Thermo that will basically explain how the Orbitrap works for those who are not familiar with it. So this is like a commercial like kind of video. So it's like mounted with a normal electrospray source. And then you will see that basically, so when the ions are produced, so here with an electrospray, they are transferred into what we call the S-lens. Then after they go until the flat apple, this flat apple is used to remove all the neutral gases. And then after it goes into the quadrupole, that you can filter the mass if you want to do single ion monitoring, or like even change the windows of integration. So this is the ions produced, so they go to the capillary, the S-lens that are used to focus the ions inside the instruments. It's a bit lagging. So then the ions and the flat apple like extract basically the neutrals, focusing the ions to the C-trap. And within the C-trap is kind of the, oh gosh, I'm very sorry. To crash again. Sorry about that. It might be the video that is crashing. So I'm gonna do different style. I will just like explain you, and you can watch the video of the Orbitrap on basically YouTube. It's a YouTube video. So what I was saying is like the ions are going in, focus on this S-lens, and then going to the flat apple, which is basically help like focusing the ions, and you remove all the neutral that go straight. Then you go to the C-trap. The C-trap will be used to accumulate the ions. And then once we reach what we say the AGC targets, so the number of ions of charge that are like accumulated in the C-trap or in the ion trap, then all the ions are injected into the mass analyzer. So then after that, the ions will basically rotate or oscillate around the Orbitrap. And then the oscillation will be recorded, and based on the transform Fourier, then the mass, the accurate mass will be retrieved. So this is why the mass resolving power of the Orbitrap is much greater due to the fact that we are using the oscillation. So this is like very unique and really help like having like a very an instrument with a very high mass resolving power. So I'm going to just switch directly to that. And what we did is we basically couple, or this we design or redesign this kind of like CI inlet, so atmospheric pressure kind of interface that you have a picture of the first one that we made here. And the principle of the CI inlet is like the same that was developed by the Hazel type of inlet, where you have the samples or the analyte that goes inside the core, the drift tube, and then you are producing in the sheet flow. So in the sheet flow, you have like in this case nitric acid going around X-ray source. The X-ray is producing nitrate ions and protons. And these ions are focused inside the drift tube, so pushed toward the center of the drift tube using a field, electrical field. And these ions are basically meeting the analytes, the neutral molecules, and they are reacting within the drift tube. And then only a small fractions of the flow is going inside the MS, and the rest is going basically outside with the total flow. So here you have the sheet flow going in, then the reaction is taking place, and then the flow is, or the exhaust is going out, and then the mass spectrometer is sampling in the core of the drift tube. So this is what we call a free wall type of inlets, because then we minimize as much as we can the interactions of the analyte with the wall of the inlet. This is why then in this kind of inlet, then it's possible to measure highly oxygenated molecules or radicals or dimeric type of compounds. So now in most of the experiments or results that I'm going to present, it's with a similar type of setups, and we run like a lot of flow tube experiments where we vary a lot the concentration of ozone, but also the VOCs. So we run at the beginning at high concentration, because then we optimize a lot after that the sensitivity of the Orbitrap by itself. But now we are running the instruments and then we are performing our experiments more around like 5 or 2 to 10 like ppb of VOC precursor, and then something around 20 to 50 ppb of ozone. We vary the residence times. So this is a picture of the setup like in Lyon in our lab, and then this is like a picture that I took when we did an intercomparison with Thorsten Bernd at the Tropos Institute in Germany, where we compare the state-of-the-art CI-APi-TOF with the Orbitrap. So we were comparing, and I'm going to present a bit later the results from this intercomparison campaign. But most of what you will, the results will have been produced like that. So mixing VOC ozone in a flow tube under varying conditions like NO-SO2, humidity, and so on, then to explore the capabilities of the Orbitrap. So when we did the Orbitrap, it's probably one of the first figures that we did was to plot the signal that we observed from our first experiments. So this is in red, the ions that were recorded with the Orbitrap from the oxidation of alpha-pinene, because we started directly to work with alpha-pinene and limonene, which was like two systems that were well known or are well known to produce highly oxygenated molecules. And then in red, then you can see the signal of the Orbitrap. Then you can see that, and for people who are doing like a mass spectrometry, they can see that the peaks are very, very sharp. And then we try to compare what with the peak width of the that will be observed with a TOF mass analyzer. So at that time, we didn't have APi-TOF or CI-APi-TOF to compare to have a direct comparison. So we simulate how wide the peak will be if we were using a TOF mass analyzer with a mass resolving power of 5,000 or with 10,000. So you can see that basically with 5,000, there is like completely peaks that you can easily miss. So for this one or this one, with the Orbitrap, all of the peaks are very, very nicely separated. And what it means that you are able now to retrieve the composition very accurately. And for instance, to be able to separate, to distinguish the organonitrates that the peroxy radicals that are formed from the oxidation of VOCs in the presence of NO. So in this case, at the mass to charge 357, which contain nitric acid, so you can see that you can clearly distinguish these radicals, the C10H15O10 cluster with nitrate, to the other organonitrate that are formed from the oxidation, from the reactions of peroxy radicals with NO. And then you can see that, like, using that, then you can really track how the concentration of individual ions will evolve as a function of NO, for instance, to probe how NO will disturb the product distribution and so on. But when we were doing our test, we realized that, like, the Orbitrap has a disadvantage. And this disadvantage, we realize it by measuring the ion intensity of the isotope, and then we compare it with a theoretical value. Meaning that if you have a compound at the mass, for instance, C10H15 or 13 or 10, then you will measure the abundance of the C9 or C10 compound, but with a carbon 13. And by comparing the abundance that we measured and the one that is based on the abundance of the parent ions, then we were able to highlight the fact that the instrument is not linear. This is basically what we show is, like, as a function of the signal intensity, or if you want to say like the concentration, because here you just multiply the normalized signal by certain calibration factors and you get directly a concentration. So we can see that, like, when we go to like very low concentrations, then the sensitivity of the instrument or this ratio is wrong. So in the perfect world, then basically you have a straight line here, while with the Orbitrap, then you can see a sharp decrease when you go to lower and lower in concentration. So it means that if you are measuring like very small concentrations, then you will underestimate the concentration of those species, because you will only see like 20% of the true signals. So by playing, as I said before, when we started with high concentration, but then now we playing a bit with the parameters. So especially with the number of charge that we accumulate in the C-trap, then we were able to push forward the kind of linearity of the instrument. So you can see that, like, when we accumulate like 5 10 to the 4th or 1 10 to the 6th, then the linearity, the instrument is more linear towards like lower concentrations. And then our colleagues from Helsinki also continue to push on these directions. And then by accumulating, so based on the number of charge, but based on the number of also microscans, so which is basically 1 microscan correspond to 1 ion injection. So if you also accumulate the number of injections that you do before obtaining 1 data point, then you can also help pushing the limit of the instrument. And then with this kind of very specific license and configurations, then you can see that, like, basically you can go to almost 1 10 to the 5 in terms of like linear answer or response of the Orbitrap. So it means, like, we can really, by playing with the condition of the settings of the Orbitrap, we can really push forward this problem of linearity. So during this intercomparison that we did at Tropos, so we also observed that. So here is a comparison between the peroxy radicals from the OH oxidation of alpha-pinene. In black, you have the signal recorded by the CI-APi-TOF, and in red, in the open circles or open markers, is a signal recorded by the CI-Orbitrap. So you can see that, like, basically when the concentration is relatively high, so 10 to the 3 or 10 to minus 3 or 10 to minus 4, then the Orbitrap is directly capturing properly the concentration of the species. But when the concentration goes like to low or when the compounds are in very low abundance, then you can see that a deviation of the Orbitrap compared to the CI-APi-TOF. So to avoid or to try to correct directly for this lack of linearity, what we did is taking advantage of these curves. So this fits. So we fit with a signal function this all the data point that we obtain, and by using this function that we determine experimentally, then we were able to correct. We were able to correct for the lack of linearity of the instrument. So basically, the open circles are the corrected value, and then the black one, the full one, are the uncorrected. And you can see by doing these corrections, then we can still push even forward the linearity of the instruments. So you can see that, like, for instance, for this species, which is the C10H15O7, 17, sorry, then you can see that, like, you can really correct and be in very good agreement with the CI-APi-TOF. And overall, if we compare as a function of concentration now, then you can see that, like, the data are nicely into one-to-one line, plus or minus like something at 20% or 30%. Then you can see that, like, even for very low concentration, so 10 to the 5, so which means like 10 ppq or 20 ppq, then the concentration of the analyte can be correctly captured by the Orbitrap. So a unique advantage also of the Orbitrap is to perform MS. So when you have the ions, so when they are accumulated in the seed trap, you can send all these ions into what we call a collision cell, where the ions will be facing nitrogen, and then this basically you will hammer the ions with like with a gas with accelerating nitrogen, and this will fragment the molecules. What we call like MS analysis. And by using that, then we can observe different fragments that allow us to determine what are the different functional groups like present in the molecules. And for instance, when we did that with the peroxy radicals, and we found like a unique loss of like O2 that are present only when we study like peroxy radicals. One advantage of that is also to probe the collision energy of the cluster. So by just injecting in the collision cells, like different kind of molecules from O2 to O6, for instance, and then by step by step increasing the collision energy within the seed trap, then you can probe the binding energy of the adduct forming the molecules. And this is quite important, because when you want to have basically a quantitative measurement, then you need to know if the ions that you are forming are strongly bonded with the analytes that you are measuring. And this is like basically following what like the group of Joe Thornton have done with iodides. It's applying the same like the same methodology to try to see like to determine at what is collision or what is energy, binding energy, where you can assume that the ions are strongly binding and won't decluster within your mass spectrometers. And then what we calculate is that it's probably somewhere around 35 to 40 kilocalories per mole. Below that, then you have to be cautious about the true concentration that you are measuring, because one fraction of your ions might have been like might have fragmented while traveling inside the mass spectrometers. So basically, with all this development and then this help of our colleagues from like Tropos University or Tropos Institute, PSI, and also the University of Helsinki, Mikael Hörn, then basically we were kind of able to develop this the CI-Orbitrap that has a mass resolving power in our case of like 140,000. A detection limit of like something around 10 ppq or 10 to the 5 molecule per cc, and also the unique capabilities of doing MSMS. But when we were acquiring all of this data, then we were facing also one kind of problems that was like linked to the data that we were generating. Because it's important to keep in mind that Thermo Fisher is developing mass spectrometer for offline analysis and LCMS. So all of the requirement that we have to analyze data, like doing pre-averaging, recalibrating, background subtraction, and so on, are not the tools that is provided by Thermo is not really capable or like very useful or handy to for the data that we are generating with the CI or later on with the easy inlets. So what we did at the end of 2019 was to also develop in collaboration with with our colleagues from China, especially from the Shanghai Institute, to develop a new software that we call like Orbitrap. So Orbitrap is a open access software that you might download if you are interested in like Orbitrap technology, and then is able of like doing a few kind of like very simple but very handy type of analysis. So it's extracting, getting the raw data obviously, then you can average, and during this averaging, then you are also creating a lot of noise, because then basically by averaging, then you are summing kind of the ions, and this is creating the some noise. So what then we develop a denoising procedure, because as you can see that this is like an example of the number of ions that we kind of, or number of peaks detected as a function of averaging time. So on this, on the figure A, then we don't average anything. So the software was able to determine like something around 700 to 800 peaks. And then after averaging 5 minutes, then it goes over 1,000. 30 minutes, it goes over close to like 10,000. And then if you go even to 60 minutes or 1 hour, then it goes like close to 30,000. And this is like mainly due to the fact that like by averaging, then you create noise on the artificial noise. So by doing the denoising, meaning that we are then we are applying different kind of like techniques to remove the noise, then you can see that we keep the number of peaks detected by the instrument like in a bit more in a reasonable with reasonable numbers. And then even if you go to 60 minutes, from 5 to 60, then the number of peaks remain more or less the same, like close to 1,000. So that means we are like 1,000 peaks in our case. In this example was most likely the kind of optimum or reasonable numbers of peaks of ions detected by the instrument. So after this denoising part that we recently optimized, because I mean, if you're interested, then we can discuss later. But then the first version that we did was not optimal. So now we developed a new procedure to denoise that, and then after that, then we can do peak fitting. Then to determine the peak width and the resolution of the instrument, we obviously can do mass calibration, do some automatic peak assignments based on like some different kind of criteria that you might use, and then we can directly get the time series of the ions that you are interested in. So this is very, very handy and was at some point needed, because then we were like looking at the data in a more continuously way through laboratory campaign or also field campaign. So without these tools, then it's kind of very extremely time consuming to analyze Orbitrap data, especially if you're in the field, because then you will need to extract the ions 10 par 10 with Excalibur, which is the software that is provided by Thermo. So with all these kind of developments, then we are basically working in 3 different aspects. So we are developing new reagent ions because by taking the advantage of the resolving power, then we can use new kind of reagent ions that are non-selective almost, so able to capture a very wide range of compounds. We are also exploring the performance of the Orbitrap in the ambient conditions. And then for more laboratory or more fundamental research, and we also look at mechanical reactivity, or like try to determine the mechanisms and the structure of different processes, mainly based on the oxidation of biogenic. During that, then we identified also new products by basically combining the development of the new reagent ions, and then like using that, then we found also a new chemical process that I will present in a few minutes. So if we look a bit at the first part, which is the picture that I showed you before, so this study was done at the University of Helsinki, and so the idea was to try to compare also the CI-Orbitrap with what we did with the CI-APi-TOF, and then to do that, then we deployed the instrument during the Cloud 14 campaign, which took place in September, October to 2019. Where we had the first flying APi-TOF, we can claim it. It was kind of a bit like scary to watch the APi-TOF flying, but it went well, and then we were able to connect it to the chamber. And then, so what we did in this campaign was like we compare the ammonia Orbitrap, so using ammonia as a reagent ions, because as I said, like ammonia is also has a benefit of being almost non-selective, so being able to capture a very wide number of compounds. And then we compare with the instrument that were connected at the cloud chamber, so the nitrate LTOF from the University of Frankfurt, the PTR3 from Innsbruck, and the Frigao from Carnegie Mellon University that was operated with iodide. And the idea was like to basically identify all the compounds that we were able to measure with during the oxidation of alpha-pinene with ozone and OH. And for each compound that was identified with the 4 different mass spectrometers, then we correlate, and then we tested the correlation between the different species. So one species or one ion was nicely correlated, then the marker was like basically big, and then when the correlation was very low, then the marker is pretty small. And you can see that basically the ammonia Orbitrap is really capable of like being in very good agreement with like PTR3 type of data. So in that case, during that campaign, with low oxidized type of compounds, but also with the nitrate and with the iodide, especially for big compounds like highly oxygenated molecules, that basically the instrument capture well. So in other words, then the Orbitrap and then with ammonia was able to have the bridge between low oxidized species to very oxidized and like dimeric type of compounds. That was very nice to see, because it's like kind of not so frequent to have an instrument capable of like covering the almost entire range of OVOCs. And this is basically highlighted by this like revised version of the plot, where you have like in dash blue, then you have the CI-Orbitrap operated in ammonia mode, and then also we plotted the other type of like instrument, PTR3, the nitrate, I would like to note that the PTR3 was like operated to measure like more ammonia, so the performance is not what you can expect. So it means like normally the PTR3 will be able to measure like more highly oxidized molecules, but in that case, for this campaign, it was tuned in a slightly different way. But otherwise, like, yes, then we continue. We found that like the ammonia's Orbitrap was very promising for measuring a lot of compounds. So the second aspect that we developed or that we tested was to explore the performance of the Orbitrap in ambient conditions. And to really test the Orbitrap, then we decided to deploy the instrument in Shanghai in 2019. So it was not our instrument, but basically right after the cloud campaign, then we flew directly to Shanghai and then to start a field campaign there and start measuring in ambient conditions. So it's not our Orbitrap here, but it was the inlet that was used in cloud, so directly after. And then during that time, it was International Import Expo. So it was very interesting because before we started the campaign, when we started the campaign, the air was like kind of normal, no restriction and so on. But then during the expo, then strict restriction were ongoing. And then after the expo, then we continue measuring. So we had basically a clean event. And then like in between two different kind of normal Shanghai air pollution. So as I say that here you have basically kind of the overview of the whole campaign. So we have this P1 period that is like right before the emission control. Then you have the P2, which is the emission control. And this is a very strict P2S, is very strict emission control. And then after is like non-control, and then that we use as a reference because we found out that later that during the P1, so right before the expo, Shanghai experienced like a heavy dust episode, so it was not really like used as a reference. And as you will expect during emission control, then you can see that the NOx went down quite a bit, almost no NO, for Shanghai conditions, almost no NO, and then ozone stay at higher level. So we were able to measure basically the effect of this kind of like emission control versus like kind of reference period. So taking the Orbitrap, so that was operated in nitrate mode, even though I said like the ammonia is like very nice for capturing a very wide range of compounds, but at that time it was way too challenging to deploy the ammonia because ammonia has some limitation as well. So we also decided for the first time to go with a simple or simplest reagent ion to use, which is the nitrate. And this is basically a mass defect plot of the average mass spectrum obtained from this campaign. So you can see that the mass spectrum is like very complex with like different kind of family from like compounds with low oxygen numbers to like compound or nitrogen containing species with a dB value from like almost like unsaturated saturated to unsaturated compounds, like more like type of or aromatic type of compounds. And then what we did to basically try to resolve and try to understand this highly complex MS data, then we run PMF. We run PMF to try to simplify because at first, then it's always good to know a bit what's going on. And then with this kind of like thousands of peaks identified by the Orbitrap, it will have been like very time-consuming, extremely complex to get some like overview of what was going on during that campaign. So the PMS that we performed was like we split it in 3 different mass ranges to also be less impacted by the volatility of the different products that we were measuring. So Yanjun Zhang actually published a paper on the effect of the selection of the range like earlier, like 1 or 2 years ago. And then she was able to identify like something about like 9 factors. So new particles events, some monoterpene, aromatics, day and night, and so on. So I'm not going into details on all of these different factors. If you're interested, then I hope her paper will be in a few months like out, and then we can obviously discuss later. But then basically by doing PMF, she was able to nicely distinguish different factors. And then when we compare between the different periods, so here in the pie chart, then you have the fraction of each different factors that has different colors, and then we were comparing like with the reference period, how basically the dust event and then the restriction and the very strict restrictions evolve or like impact the different factors. And then a nice way of looking at it will be to look at the factors that was basically reduced and the factor that was increased. So then like some factors was like really immense. So for instance, like during like the P2S, so the strict emissions period or strict control, then you can see that the monoterpene, so more like biogenic oxidations, like highly oxygenated molecules that we identified, and also all of these new particles event, like more iodic acid, sulfuric acid, and so on, went up by like 100 to 200%. In the other directions, then you can see that the more like compounds that were produced from like direct emissions, like aromatic or alkanes, were greatly reduced by the emission. Okay, so now if we go back a bit to like more fundamental type of research, and then we look at like what the Orbitrap can tell us in terms of like structure, and then how can we help like better understanding the chemical mechanisms. So to explore the basically these new features that like the Orbitrap is offering, then we were again like studying the ozonolysis of alpha-pinene. Because as you can see, the ozonolysis of alpha-pinene will produce like different kind of radicals, and those radicals can evolve into many different ways. So basically what we discussed with A root, D root, C root, and this ring opening route. So basically by doing that, then you can see that the structure of the radicals and also the closed shell product that will be resulting of the big molecular reactions, and you can see that the structure can differ quite a bit. And the fact that the structure differs means like you will have different volatility or like reactivity later on. So what we did is like, so this is like overall mechanisms. And if you go to like even the C10 compound, then you can see that like you get like a lot of different possibilities. So what we did is we did MS-MS with the radicals, which was like at the first, it was not very, we were not 100% sure it's going to work because radicals are extremely reactive species. But at the end, it turned out that it worked pretty nicely. And by studying basically the fragment science that you can see, like for instance, for the C10H15O8, then we also try to ramp up the kind of collision energy to see what is, if like by changing the collision energy, we can learn more in terms of the structures. So when we perform the analysis at low collision energy, then we were able to retrieve some very important fragment ions, and using these fragment ions, then we are able to retrieve basically the chemical structure of the radicals. Of course, we cannot be 100% sure because different isomers can be present, and all these isomers of the fragments, the MS-MS spectrum will be the sum of all the different isomers, but then at least we can derive some tentative structure or the most likely structure that we think based on the analysis of the MS-MS data. So based on that, then basically we were able to, if I go back to the mechanism, to pin down like the most likely structure that we propose from the auto-oxidation of alpha-pinene. So for instance, if we take this one, then only this kind of structure, or mainly this kind of structure, can explain the fragmentation pattern of these O6 radicals. By using also still the MSMS, then we were also able to explain very interesting features. Then we compare between alpha-pinene and limonene. So basically, if you compare the distribution of the radicals, so here you have the radicals of 6 or 8 or 10, and then the relative abundance that we basically scale based on 08. Then you can see that the product distribution or the radical distribution is pretty much the same between alpha-pinene and limonene. But if you look at the dimers, so basically the closed shell product from the bimolecular reactions of the radical, those radicals, so the C20H30, then you can see that the product distributions will change dramatically. So here we scaled it based on the O14, but you can see that the dimer formed from the alpha-pinene will be less oxidized than the dimers formed from the limonene, even though the product distribution or the radical distribution remain the same. This is like what we explain is, or what we think the reason is that like for the formation of the dimers, the OH radicals is more involved in the reaction, and this was like demonstrated by the MSMS data that we obtained from limonene and also alpha-pinene, because for instance with limonene that you have here, it's the same, the mass to charge, and then the fragment ions or the MSMS spectrum from like for different ions. Then you can see some fragment ions with O7, so for instance this one and this one, that indicates the importance of the OH radicals in the formation of those dimers. But if you do exactly the same with the alpha-pinene, then you won't see these fragments. It means basically for forming this O14 kind of compound, then the O4 radicals will be involved. So it means in sum that like the reactivity of the limonene and alpha-pinene will be completely different, and the importance of the O4 for alpha-pinene will be higher than the O4 for limonene. So by using this kind of like MSMS features, then you can really better understand which radicals will be involved in the reactivity or in the formation of dimeric type of products. And then the last part that I would like to highlight, so I skipped 4 and go directly to the 5th, was like again, still the oxidation. I'm sorry that I'm talking only about alpha-pinene, but it's true that we have been working quite a bit on it, is basically the competition between NO3 and ozone chemistry. So during the flow tube experiment, also like cloud experiments, then we were like simulating the transition between kind of day to night or like night chemistry. And what we found is that, so when you have basically ozonolysis of alpha-pinene, which is basically in the red here, that's the abundance versus the mass to charge, then you can see the product distribution of like the normal kind of ions, so radicals and closed shell products from different pathways. And then when you start adding NO3 in the system, then you can see that like obviously the product distribution changed totally. So what we found is like basically you shift towards like less oxidized species, and the dimers that are presented here, we go from O10 to O16, then you can see that all the dimers shift from like to low oxidized species. So we look a bit more into the product distributions as a function of like reactivity of nitrate. So here you have the evolution of the concentration of the normal arms, so closed shell molecules, but also the normal dimers from like alpha-pinene or ozonolysis. And this is in a x-axis, that's the percentage of the reactivity of NO3 to the total alpha-pinene reactivity. So at 0, it's basically pure alpha-pinene ozonolysis. And when you start adding NO in the system, when NO starts to contribute more and more, then you can see that the concentration of the species, especially the most oxidized one, goes down by quite goes down significantly because it's a lot scale. And then the more interesting aspect will be the dimer, because when you start going down in concentration, or when alpha-pinene, the nitrate oxidation of alpha-pinene starts to be more and more important, all of this nitrate goes away. But the normal, all of the normal type of dimeric produce goes away. And then another way of seeing that is, this is another evolution of the alpha-pinene nitrate reactivity. On green, the green markers are the normal dimers, so the C20, H30, and 32. And then on orange, you will have the nitrogen-containing dimers or organonitrate dimers. And then this black and red correspond to the nitrates or R2 formed from nitrate chemistry and R2 from ozone chemistry. So the first thing is the reactivity of alpha-pinene from ozone remains more or less the same. So the same kind of radicals produced from ozonolysis, but you can see that the product coming from the reactions of these H15 radicals, which are the H30, goes down dramatically. And then what takes place is the dimers formed from the NO3 reactivity. So basically, by adding a bit of nitrate radicals in the system, you switch completely the product distributions, even at very small concentration of NO3. Because in this case, it was something around 10 ppt of NO3 injected in the system. And then we check also what happened during the cloud campaign, that we had one run with NO3, what we call NO2 or NO2 diplodocus or NO3, where you have stable conditions before. So it was, in this case, ozonolysis of alpha-pinene, so stable conditions. And when we started to inject NO2 in the system, so NO2 will react with ozone in absence of lights, and then will form NO3 radicals. The NO3 radicals are simulated in here and goes to something around 0.6 ppt. So very small concentration of NO3. Ozone remain constant, alpha-pinene remain constant, and what we observe is basically the same as in a flow tube experiment, that the dimeric products, the highly oxygenated products, as soon as you start producing NO3 radicals, then they are basically scavenged, or they go away to almost to zero below the detection limit, and the less oxidized species goes also down. And what takes place is the most oxidized, or the compounds coming from nitrate radical chemistry, so the dimeric product from, in this case, the H31O7 with a nitrogen containing, and then the dinitrogen, so the diorganonitrate dimers. And the resulting effect of all of this modification of the chemistry, and especially at very low, again, very low concentration, because here we talk about half a ppt, around one ppb of alpha-pinene, that's a very sharp decrease in the particles formations. So you can see that when we started to inject NO2, then you have a very, very sharp decrease of the number or the production of more particles. Another way of saying that is that you have alpha-pinene plus ozone here as a function of formation rates, or J rates as a function of diameters, and you can see for particles from 1.7 to 6 nanometers, and as soon as you start adding 0.2 ppt, 0.4, 0.6 ppt of NO3, then all the concentration drops, or the production rate of new particles drop significantly. You have the same kind of things with different J rates from different size cuts, and as a function of NO3 concentration. So even a very small concentration of NO3, then the product distribution is so disturbed, and then the formation of this organonitrate taking place is really killing, or reducing sharply the production of new particles. This is like partly explained, even though I'm not 100% convinced, or like I'm not convinced at all that we capture properly the volatility of the organonitrate. But then you can see that what is like dramatically dramatically kind of impacted is the U-LVOC, where the on alpha pinene plus aldone, and you can see that like it corresponds to something around 34% of the total oxygenated species measured by the nitrate, by the ammonia CI. And if you look at like under like at this, basically these conditions at 0.6 ppt, then the contribution of this ULVOC like drops significantly by like almost a factor of 2 to 3. So this basically modification of the chemistry was like captured by taking advantage of the ammonia arbitrage. Because before, like observing all the product distribution and also being able to measure the radicals and the less oxidized radicals was not possible. So before terminating this this seminar, I would just like to basically introduce that we also develop, or the CI-Orbitrap or the Orbitrap technology is not only for gas phase, obviously. But we also developed a particle phase inlet, especially with our colleagues from PSI and Imad El Haddad. That is basically we developed extracted electrospray inlet that is basically coupled with the Orbitrap. So this kind of technology, if you are not familiar, is like very nice for extracting without thermo decomposition or thermo evaporation the aerosols. So you just impact the small aerosols into a big electrospray droplets. Then you the soluble fractions will basically be extracted in the droplets, and then the droplet will be evaporated. And what we will obtain is the oxygenated species cluster with in positive mode or in negative mode, depending on the mode that you are using. And basically, by using this this technology, then we were also able to achieve like high mass resolving power. Obviously, very good sensitivity. So we are close to like 1 nanogram per cubic meter, or even below that. I guess we can even push further, but it will probably require more optimization. Obviously, we can do some MS analysis, and we did not observe any matrix effect. And then this coupling is also limiting the disadvantage of the EZ-TOF, which is the background, because the EZ-TOF works very nicely with probably a better sensitivity, but the background is a big issue. While in that case, and in general, the background is not a problem with the Orbitrap, because the resolution or mass resolving power helps like resolving this background. And then basically to conclude, I would like just to say that like the Orbitrap is like either for CI or easy is for sure a very powerful instrument. And I hope like will help us like better understanding gas and particle processes. Thank you for your attention.
Thank you, Matthieu, for the very interesting talk. And I'll let the seminar run for 5 more minutes because of the technical difficulties that we experienced, so people can so we can see if we have some questions from the people from the streaming, and people with the Zoom, they can ask questions now if they want to, or they can wait until the recording will be off, and we'll have a session with you, Matthieu, and just free questions offline. Okay, let's see. I don't see I don't see the screen from the Slido. Okay, no questions at the moment, it looks like, which might make the waiting of 5 minutes unnecessary, but yeah, I'm really fascinated about this this technology of the Orbitrap, and you seem to have already found and solved some issues, and I've been wondering a lot about the artifacts due to the optics of the instrument. If you would like to comment on that, if you have noticed any issues, because compared to the TOF, the ions need to go through quite some stuff before they get detected.
So the acceleration of the transition from atmospheric pressure to low pressure, it's an issue for any mass spectrometers, basically. I can actually show you, let me just take I will just show you again my slide. Oh, I will do that like that more. So basically, when we did that, we had not like a film like conclusion, but like we compare the less oxidized species observed with like the APi-TOF technology, so TOF technology, and then the Orbitrap. And if we do that, then we can see that like the less oxidized species seems to be less impacted than in the APi-TOF. So if we do, let me just pull, yes, this one. If you compare, for instance, this, so if you compare this O2 or O3, so which is a radical, so you can see that like with the Orbitrap, the sign or the concentration that we calculate is higher than the concentration retrieved by the APi-TOF. And then if you compare with a more oxidized species, then it's going to be the opposite way. The APi-TOF will see more, the concentration will be higher than in the Orbitrap. And the difference here is that we think, or we propose, that is just because the transmission of the ions inside the Orbitrap is softer than in the APi-TOF. At least in this APi-TOF that was tuned in this way, because obviously you can tune the instrument as you want. But in our case, there is also room to play with the instrument, the S-lens, basically the focusing of the ions right when they enter the instrument. And that we play a bit, we tweak a bit these parameters. But at least in these conditions, it seems like the ion transmission is softer in the Orbitrap compared to this APi-TOF again.
Very interesting. Yeah. So, Brad, if you could show me the Slido once more, and if we don't have any questions, I will go ahead and say goodbye to the people in the streaming land, and see you next time. In 1 week, we'll have another seminar. Please join us. This time is going to be the usual time at 3:30 p.m. Mountain Time. Thanks for joining. See you next time.